All right. Hello, community. Hello, RaySearch webinars community. So nice to see so many of you today. It's so we are now located in Sweden. So we are here with the sun in this morning. Some of you, of course, are having in the afternoon or at any time. We're just super happy to have you here in this second session of the Artificial Intelligence in Cancer Care webinar series. So we had very excited and very interesting session last week. So whoever is joining us after the first one, welcome back. If it's your first time with us in the community of RaySearch webinars, well, welcome as well. We have a recording of the first session available on our website, so you're more than welcome to come back there, watch that, and then we will do the same thing for this session as well. All right, so before we jump into today's topic and today's webinar, we tried something new last time, and that was some live polls and uh, and live questions, and we liked it because it gives us the chance and opportunity not only talk ourselves, but also to get you better, to get to know you better. So let's start with a warm-up question. So we have it here, a warm-up question. How do you expect to feel after this session? Because I know we all have a lot of expectations in general in life. And to have a good session and to have a good result, I always think that expectations should be aligned. So let's do that. Let's see how you are feeling about your expectations after today's session. So we have a couple of options. So are you feeling inspired or you expect to be feeling inspired after the session? So you just want to see what's next for AI in planning? Do you want to feel informed, so deepen your understanding? Do you expect to just feel like mildly impressed? Because you will need to see more evidence, or maybe you're just gonna feel hungry. Probably I'm gonna be in this in this team because webinars they do make me snacky. I need to be honest here. So right, so that's the options for you. I see many of your results coming in, and let me share that with you. All right, so most of you are expecting to be more informed after the webinar and inspired, which is good. And this is what we'll try to deliver to you over today's session. And let me just jump straight into the session for today. So, what do we have today? Today we have AI in radiotherapy planning. So that's, as I said, the second session of the Artificial Intelligence in Cancer Care webinar series. And we do have presenters, of course. So the first presenter is our Fredrik, Director of Machine Learning. Good morning, Fredrik.
Good morning, everyone. Nice to be here.
And welcome back, I must say to you.
Thank
But we
you.
also have a new presenter joining us today, and that's Christian. Christian, hello.
Good morning, everyone.
Hello. And so, yeah, I'll be here doing the same thing as I did the last time. So my name is Marta. I work here as marketing communication specialist. And I'll also gonna try to launch this polls and moderate the questions that we will have. And when it comes to questions, we do have our experts joining us today as well. And we even have more this time. So instead of three, we have four. And let me start introducing them. So the first one is Jacopo. Hello, Jacopo.
Hello, good morning, everyone.
Hey, we also have Gabriel. Yes, and then Danny.
Good morning.
Hey, Danny, and Jason, who is joining us again. And Jason is the one who's representing the quality assurance site. When it comes to development, so for development, we have Jacopo and Gabriel today, since they are both in the ML planning development team. And then Danny is our clinical voice, I must say, today, as he is the application specialist for machine learning planning at RaySearch. So we have four people to take care of your questions, which means please go ahead and ask as many questions as you would like in the Q&A section that we have open throughout the entire presentation. So we make sure that all of your questions, or most of them, are being answered on real time. So the more you bring us, the more we're gonna bring you back. That's the rule. All right, so let's go to the next poll. And that's going to be the one that just a warm up, but more about the topic of today. So for this one, I would like to ask and see about your experience of the AI-generated dose distribution in patient case. Have you ever seen a dose distribution in a real patient case? Just for us to get the sense of what level of experience we have here. And it doesn't matter if what experience we have, because we will go through a bit more on the educational level here and just to try to get everyone on the same page. All right, so it's a very simple answer here. It's either yes or no. And then let's see what's the distribution here. And here we have that more of you actually have never seen the AI-generated dose distribution in a real patient case. And that's 70% of you who answered and 30 have seen it. All right, so we'll take that into consideration. And Fredrik, I think it's time for your part and where we will hear more from you. So good luck.
Thank you, Morta, and thanks everyone for joining. I will. Some of you were probably here last week, and listened to that webinar. And the first 4 slides I have will be the same, so bear with me. The rest will be new. But these introduction slides are a little bit to set the context of automation and AI in oncology. So, looking at the background, we have a situation in the world with aging population. We have a shortage of healthcare providers, and this combination, and also more kind of complex treatments coming up. This becomes a problem, of course, with succession planning, but also stress levels at the clinics. And there is a very large need of basically automation and resources here. AI in healthcare can be part of this solution. So AI can help automate and streamline many of the tasks that happen at the healthcare providers that they are handling daily, and that saved time can then be used to in a better way, I would say, than repetitive tasks. For example, direct patient care, reducing stress levels, and there is, I mean, as of today, a majority of healthcare providers support using AI in daily practice. So the question for us as a vendor in this field is how can we respond to this AI potential? And before going into that, I want to just set the stage in terms of terminology here. So while AI is the wide concept that I mean, is everything you see and hear today about AI in the news and ChatGPT and everything. Machine learning, we see it as a subset of AI, where we train models based on some data. And in oncology, it can be RI contours or dose distributions. And such a model that has been trained, you can then predict and generalize to unseen cases. Then a subset of machine learning, and I mean, that's where we are. It's deep learning, and that's about neural networks that can then be applied, for example, to medical image data. So machine learning at RaySearch. So we started in 2017. We have been working on this for 8 years, and we are about 30 people now, focusing on AI development in oncology and cloud technology and infrastructure. And we have not only, I mean, worked on this, we have put this in production. I will come back with a timeline a bit later on, but since many years, we have our AI in production at cancer clinics around the world. And the 2 products we have released is deep learning segmentation, that was the previous webinar, and deep learning planning, which is this webinar. So I wanted to put some background into this topic. Maybe you're not all coming in from the radiotherapy or even oncology field. But I wanted to kind of try to describe what is automation, automated treatment planning, radiotherapy, and then what is the AI part of this. So looking at the radiotherapy planning, so what we want to do is to basically create a treatment plan for delivery to treat, cure, or palliatively care the patient. So the input data here is the patient geometry, and here the structures, of course, could have been automatically generated with deep learning. Then there are some other input parameters, such as the clinical goals. How should we treat these patients? The dose to 98% volume should exceed 57 gray, for example. What is the delivery technique? It's VMAT is one option here, for example, and that also then belongs to, okay, it's a photon-proton treatment, and what machine do we have? What is the beam setup? Which angles will they hit the patient? For VMAT, maybe there's a dual arc treatment. And what's the prescription? Yes, we want to treat with 60 fraction or 60 gray over 25 fractions. So these are like the input information for creating a treatment plan in radiotherapy. Then there is some kind of automation, and then there is a deliverable treatment plan or plans, because maybe we can, with automation, generate multiple plans. And that has, since it's automated, it's offline, and it's fast. We have the luxury to do this. If you do the plan generation manually, you typically don't have this luxury. And then there's a qualified user at the clinic reviewing these plans, refining if needed, or selecting a plan, doing the quality assurance and delivery it for the patient. So the key here is that there is an automation step taking the input to deliverable treatment plans. And if we move then to AI, how does AI come into this automation flow? So, well, we have some of the input we saw on the previous slide: patient geometry, prescription, beam setup, possibly beam setup. Maybe you have it, maybe you don't have it as input to the AI model. Then we have what we call a dose prediction model, taking this input and predicting a dose distribution, a 3D dose distribution for all the volume elements in the patient based on this input. Then we add some of the other input we had before, such as clinical goals, delivery technique, beam setup. Then we do an optimization that we call mimicking optimization. I will come back to what that means. That is not AI. That is old-fashioned gradient-based optimization, large-scale non-linear optimization. And then this is the automation. So as a user, you would not see this explicitly happening, but you would define these blue boxes in one way or another. Maybe you script it, maybe you automate it, maybe you run deep learning segmentation. But once you start this optimization or machine learning planning, this green box is happening automatically. Then deliverable treatment plans are generated, and then the qualified user come in and do exactly the same thing as for any treatment plan, if it was manually created, automated created. So this is trying to summarize, okay, there is two steps in this automation that we have implemented clinically. There's one AI part, and that's dose prediction. There's a non-AI part, and that's the optimization. And if this was not enough, I wanted to also say some more terminology here, because I think this will be useful when Christian also enters this webinar in a couple of minutes. So we refer to a dose prediction model also as a ML model. Words for the same thing. So that's the neural network taking the input, predicting a dose. An ML model has a scope. It was trained on data for a certain protocol, a certain beam modality, a photon or proton, for example. And this ML model is validated in-house by us and locked before market release. And what I mean with locked is that we will not touch the weights of the or parameters of the neural network once released. That is fixed. So same input would generate the same output. Then we have the second part, the mimicking optimization. So that is basically a two-step, we can picture it as a two-step approach. So first, you set up an optimization problem combining this predicted dose with the clinical goals or the preferences of the user. So the predicted dose is kind of part of the problem formulation of this optimization problem. And then you solve this problem taking very importantly, the treatment machine constraints into account, so that the output, the result of that optimization, is a deliverable treatment plan. And this is kind of what we have done at RaySearch for 25 years. This is where we started in 2000. And so this is kind of core knowledge here in-house. Then we have a term that we will use later on, configuration or maybe model configuration. This has nothing to do with a deep learning model, actually. It's about step one above, setting up the optimization problem. So this is done during the commissioning process at customer site, and Christian will talk more about this. The purpose here is to incorporate local preferences into the optimization problem. So while the neural network will be fixed, will output a dose, as with any optimization radiotherapy, you can put your own requirements or preferences into that optimization problem, and then you get some variation in the output there. You can kind of configure or steer that optimization to your preferences. Yes, and my final slide in this introduction is kind of a history of what's been going on here. So evolution of deep learning planning at RaySearch. So it all started in 2017 in second quarter. So that was basically when we established the machine learning department here. We collaborated with Princess Margaret Hospital in Toronto, and it was all based, I would say, on the work by Chris McIntosh and Tom Purdy there. And there's a reference down there on dose prediction with Atlas regression forests. So this collaboration was basically, there was a prototype, and we collaborated on this to turn that prototype into a dose prediction model, basically, that could be integrated into RayStation. So 2 years later, there was the first clinical release, and the first clinical use was shortly thereafter. Then with the, involvement in technology in this field, in 2021, we basically developed and released our first deep learning models, so 3D unit convolutional neural networks for dose prediction, and there's a reference down there as well. And then from there on, all our models are based on 3D units. A big milestone for us was the first proton model in clinical use, and that was in Q1 22. And then we reached 1,000 clinical treatments with deep learning planning in 2022, and then 5,000 in Q4 last year. So this is a rough timeline of what has been going on, and it's I think it was also very fun to create this timeline and to see what the progress has been. But it's been super fun to work with this and see the development. So I hand over back to Morta.
Yes, thank you. All right, so thank you for that introduction. So by seeing the first poll results of that 70% of you who are here with us today have not ever seen the AI dose distribution in a real patient, set us this on the same level and gave us a good background to build on. But then since most of you have not seen it, let's talk about, again, expectations and what would we expect from the AI performance of the planning. So the first question that we have here for you is, how complete would you expect an AI generated plan to be? So we have some options here for you. So anything from 100%, saying that fully ready without any manual adjustments, maybe around 95%, so almost ready for clinical use, around 90%, so minor fine-tuning expected, around 80%, moderate manual edits required, or we go down around 50%, where we are leaving ourselves at the significant manual work still needed. Then, so that's the first question about the expectations to AI model performances in planning. Now, the second question that we would like to ask you is the first cancer site for a fully automated planning. So let's say you would have access to have to a deep learning model. So what treatment site would you choose first? Would that be for prostate, head and neck, breast, lung, rectum, brain, liver, pancreas, or gynecologic. So you have these options to choose as well. And scroll down, you see all the options if you do that. We gave you many to pick. And then let me share the results with you. So when it comes to completion or how you would expect the AI generated plan to perform, you would say that around the majority of you would say that around 90%. So only minor fine-tuning expected. So you leave a little bit of a gap for AI performances. That's good. And then when it comes to a treatment side, the majority of you, so 66%, would choose prostate as the first choice. So, and then after that, head and neck and breast taking over the equal amount, around 15%. Thank you so much for your expectations again, and we'll take that into consideration, obviously. But then let's talk what we might already been able to deliver on these expectations. And for that, I would like to introduce the next presenter of today's webinar, and that is Christian. So Christian, please join us, and we'll see your part. Will you talk more about the solution that we have in our house at RaySearch?
Yeah, good morning and good afternoon from wherever you are joining. I'm Christian, I'm an application specialist at RaySearch, and I will guide you through the software product of deep learning planning and how it's implemented in RayStation. And for the structure of this talk, it will be about the values that we incorporate in the development and usage of this model and in how we support our users in using that solution that we offer. So first of all, it's about dedication. And as you know, that if you introduce something that is novel, such as AI planning, it's of course never easy. And this innovation, it will require continuous dedication by a team. So although it's an AI solution, it's a team of real people, which will help us to make these models become increasingly intuitive and streamlined in the use. So here you can see the faces behind the ML planning team. And we are joined also by the machine learning imaging team and the machine learning clinical team. And what I would like to stress here is what makes the machine learning planning team special is that its members are either software developers or people from clinical background that have actually worked in the clinics. But both of these groups, they do have a solid understanding of either looking at the code, or although they are from clinical background, or looking at clinical treatment plans and data, although they are software developers. And the combination to be joined also with the clinical and imaging team is great, because this way we do have many professional backgrounds included in the daily work discussions. And this is, of course, necessary to reach the full potential of such a product to combine and to reach the best patient benefit on such a dose distribution. So we do have a lot of clinical knowledge in-house. And as I said, it's necessary to be able to reach that high quality on the treatment plans that every different profession that is also in a radiotherapy department is also reflected in our group of developers and people. So in our development teams, we do have radiation oncologists, RTTs, medical physicists and dosimetrists that look at the treatment plans, engineers with a good understanding of radiotherapy that might either be imaging, dose distributions, or anything else that's surrounding these topics. And what's also great strengths of our teams is we do have different backgrounds, but also we are from different countries. So being from different countries helps us to better understand different flavors of treatment planning, different guidelines that are used in different countries around the globe. So a team that brings this type of quality will drive innovation in the product, of course. And when we talk about innovation, as Fredrik also introduced, AI-driven treatment planning began at patient in a real clinical workflow already today. And that innovation is in many parts integrated in the product. And I will guide you through what's happening in the product in RayStation and how deep learning planning is actually used and how it works. So here you can see a typical workflow, which is started by just pressing one button in RayStation. And the machine learning planning framework starts in the same manner as you would be used to in manual planning. So you start with a CT image, which has contours on it. Those might be, for example, derived by deep learning segmentation. And these RI labels, so they are either 1 inside an RI or 0 outside an RI, will be passed to a neural network, which will then predict you a 3D spatial dose distribution that will be evaluated in RayStation, for example. So the input to that neural network is the RIs, or different RIs to be precise, organisms at risk and target volumes. And the output is a patient-specific dose distribution that is not yet deliverable. And this predicted dose is patient-specific because all the RIs contours that will be fed into the neural network are patient-specific, of course. And then this predicted dose is used as input to setting up an optimization problem in RayStation, which we call dose mimicking. And this dose mimic optimization within RayStation for a given setup will create you a deliverable treatment plan that is close to the predicted plan. And what's great about this part is here you can actually include all the information about your treatment machines, your machine constraints, leaf travel motion, monitor units and such, and your clinic-specific treatment machine as well, of course. So novelty is in many parts of this workflow. For example, we will generate a patient-specific treatment plan without any iterative steps here. Another point is you will end up with a completely deliverable treatment plan in RayStation that you can directly send to the machine or the machine that you are using clinically. And you have all of that in one system in RayStation. The benefits here are many, of course. So you can find a time improvement, but also in a reduction of inter-observer and inter-planner variability, which will lead ultimately to more standardized treatment planning approaches in your clinic. And the time that you have gained, you can, of course, use as you wish. You can either go back to refine your structures, you can refine the dose distributions, you can create multiple treatment plans for a given case if you're using different strategies in the machine learning planning model, or you can move simply to the next patient. When you decide to stay on that patient, you can, of course, use all the tools that are available in RayStation to further tweak the dose distribution to your liking. And since all of these parts are automated and scriptable, you can also use them for an adaptive workflow if you wish. For example, running deep learning segmentation, gluing it together with deep learning planning to essentially have a deliverable treatment plan in a very few clicks. So how do we develop such a prediction model? Each development project will start with discussions from us at RaySearch together with the partner clinics. And in each of that development projects, we will focus on one treatment site and one treatment protocol. So for example, prostate, 3 levels, as in the CHIP protocol, for example. And at the end of each development cycle, we will end with a thorough testing of the model. So this includes user-side testing, where our informed users will test such a model in terms of qualitative review, so manually going through all the slices, as you would do during treatment planning approval. This will be supported by quantitative testing, so dosimetric analysis of all the treatment plans, and ultimately, we will validate that model. So a typical life cycle here would be deciding on a treatment protocol, select the data that we have, train the model, test the model, validate, and release. We will have a look at how this works practically here in a bit more detail. So first of all, the first step always is to collect and review data that we will use for model training. And per model, for such a dose prediction model, we will have around 100 to 200 patient data sets from partner clinics. So when we say data here, it's actually real clinical data that was used to treat patients. So all of these clinical data is actually clinically approved treatment plans. However, we not only look for quality, which you can, of course, assume from a clinical plan, but we're also looking for consistency to train such a model. So for each of the data sets that we look at, we will go through the ROI contours and beam setups. We will formulate pass and fail criteria, whether or not to include data sets in the training, how we do handle outliers in these training sets, and which metadata we want to select and collect. And those will also undergo bias analysis for the models that we develop. On the right-hand side in the table, you can see, for example, in each row for a given patient case, the result of such a treatment plan review. So we score whether the treatment plan has passed, typically based on clinical goals. If we are looking to develop a robust model, we are looking at robust evaluation of the actual treatment plan, whether it has passed robust evaluation or not. And then if we want to exclude or include that from training, why we excluded it. And then we also add information, for example, of whether or not the organs at risk overlap with the target volume. Because this might, of course, impact how the dose distribution will look like, and therefore will also affect how the model will predict the dose. So for data selection, typical examples for metadata or patient information would be breast, chest wall, or implant for breast cases, whether or not they are post-operative, age, weight, height, etc. And at the end of this data selection, we will start to train the model, which is done in-house from us at RaySearch. And the data selection is then finished, model training is finished and done in-house. And this typically takes about 3 to 6 months to train such a model and will be done offline. And as a result, we will have a guideline-compliant prediction model. This model will then predict you a patient-specific dose based on the ROIs given on that patient case. However, the dose is not yet deliverable, and this will be covered in the second step, which we call dose mimicking. Based on the predicted dose, we want to create a deliverable treatment plan of very high quality. And this is done in 2 phases or 2 steps. So first, we start with an initial optimization within RayStation. We focus on the dose volume histograms, or short DVHs, but because this is only non-spatial information, this will be supported by optimization on each voxel. So we also look in the initial optimization on the spatial dose distribution. And then we also look at the parts of the dose fall-off to have a good match, not only in the target coverage and organs at risk, but also in the dose fall-off around that. So at the end of step 1, you have a very good plan with good overall plan quality. However, this plan is good in all aspects, but it's perfect in none. And this will be covered in step 2, where we run fine-tuning optimization. Once again, we look at the DVHs and the spatial dose distribution to push further for a better dose distribution. We specifically focus on the clinical goal fulfillment that are formulated for that patient case. And we can even push slightly beyond the reference dose. For example, if you want to be more strict on target coverage than the reference dose was, or if you want to be more strict on organ at risk sparing. So at the end of step 2, you will find perfect target coverage and the fulfillment of the clinical goals. And at the end of this, there is innovation in a lot of parts. So first of all, during mimicking, we take into account the clinic-specific treatment machine with the machine constraints. Also, the weights of the optimization functions over the course can be adapted over the course of multiple runs. So it's not only one run of optimization that you can do, but you can actually do multiple runs. You can outperform the reference dose, which will help you steer the output towards your clinical preferences. And the algorithm that we use for that is very stable and performs well on a wide range of patients. And most importantly, we will cover that later, this algorithm is also configurable to the end user. So with this, you can actually better adapt to how you do treatment planning at your clinic. Once this model is trained, and we do have a default setting for the mimicking, we can go to qualitative testing of that release candidate. And of course, what we want to do is we want to cover a global spread of user-side testers to get the best feedback possible. And all clinics that participate in such a user-side testing of a release candidate, they will review the model performance on unseen real-world data. So they will run the model that we have developed on their clinical data and send us their feedback. The idea here is that they score and comment on the model outcomes that you can see on the right-hand side table. So in each row, you find, for example, a patient case and the score for such a predicted dose. And the range of these values from 0 to 3 is 0 being the dose prediction is off and not usable at all, to 3, which is a perfect dose distribution, and you would actually consider the quality of that dose distribution to be clinical, although it's not yet deliverable. And then also the comments, you can see, for example, that the 95% of one of the target volumes is slightly missing one of the slices. So this is very valuable feedback. At the end of user-side testing, we will compile and review all the feedback that we got from customers and decide whether there's a need for improvement of that model. If it's not, we will release that model as is, or we will adapt if necessary. And at the end of this process, there will be regulatory approval, of course, before we release such a model. And then the third value that I would like to talk about is the solution ownership. So what do we offer in the product? How do we support clinical users in using that product of deep learning planning? And how do we take ownership of our product's lifecycle? So this is how you would find deep learning planning in RayStation. So the starting point in RayStation is a set of ROIs. You then go to plan optimization. You select the machine learning optimization, and then you select the dose prediction model. For that dose prediction model, you select a mimicking strategy. And here, that's of course a great feature. You can define multiple strategies per prediction model. For example, you can define one strategy to prioritize target coverage, and you can prioritize organoid risk sparing for another strategy when you wish. And within seconds, based on the ROIs that are input to the neural network, you will have a patient-specific predicted dose. And then this predicted dose will be used, beams are added, use a template or scripting, however you like, and this will be fed to the optimization problem. So the predicted dose is used as in setting up such an optimization problem in RayStation according to the dose mimic strategy that you have defined. And in the end, you will have a deliverable treatment plan that is close to the predicted dose. The runtime between creating a prediction and a deliverable dose will depend on basically the same factors as you would be used to in clinics. On the size of the target volume, on the size of the dose grid, the resolution of the dose grid, statistical accuracy, and whether or not to include robustness. So for example, for a 2-arc state VMAT case, you will find times in the order of 3 minutes. And for a proton plan with robust optimization, it's in the order of 30 minutes. But remember, this entire time is offline, so you would just need to press the start button in RayStation. And after the dose is created, you have a deliverable treatment plan, but you can also, of course, choose to select any tools within RayStation that are available to you to further optimize your plan if you wish. That includes fine-tuning, dose brushing tool. You can continue optimization. You can add RayStation objective functions, however you like. So what do we actually offer in terms of deep learning planning models? We develop models that clinical partners request and actually need. So it's not about training any model, but it's to train the most important models to our customer base. And this is also where our feedback is very important to us. In that entire development circle, therefore, we stay in close contact with the customers to ensure the relevance of these models that we are about to train and that are trained. And in that regard, we do already feature today the most important anatomical sites and treatment techniques. So anatomical sites from head to toe, it's brain, head and neck, lung, breast with or without nodes, prostates with or without nodes, and rectum. And for the treatment techniques and modalities, we do support photons and protons for VMAT, IMRT, and helical for photons, and pencil beam scanning for protons. In every release of RayStation, we do release the deep learning planning models. And over the course of the development of the RayStation, you will find that we also release new models. And all of them are fast and scriptable if you desire to have full automation in the workflow. So you can find all the released models in the catalog. In that catalog, you will find an overview per treatment site. This will include information about the training data. So this is the modality and treatment techniques. It's the primary prescription and fractionation that was used to train such a model, the number of dose levels, the clinical goals that were used for the target volumes, and the clinical goals used for the organs at risk. So for example, if you are interested in using a machine learning planning model, you can locate a model of your interest, let's say 60 gray, to one target volume for prostate. You will find a model for prostate to one dose level. So because it's not the exact dose level that is defined, but it's the shape of the dose distribution that is important in the selection of such a model. And then you can go about the adjustments of such a model during the mimicking phase, as Fredrik has introduced, to cater for your clinic-specific prescription and your clinic-specific treatment machine and treatment planning approach. And this is called model configuration. So the configuration to your local preferences. And the process of the configuration of such a model will be coordinated and done by us at RaySearch. And for this, the only thing that you need as a clinic is to provide a set of configuration cases. Typically, that's in the order of like 5 to 10 anonymized cases and a list of clinical goals that you would like to use. Of course, these clinical goals should reflect what you do clinically. The configuration is then performed by us at RaySearch. So we will tweak the model settings to cater for your clinic-specific needs, include your treatment machine, and so on. We will then send you a first candidate of a configured model to your clinic. You can then evaluate the output of a model, discuss with your clinicians, have a good discussion about what is good about the model output, what is to be improved for the model. That might, for example, include monitor units are too high, plan complexity is too high, target coverage is too low, we're missing 0.5% here or there. Organ at risk dose should be further pushed, although it is already met, but we believe that this is improvable. You will then send us your feedback and we will once again adapt your model settings. And this process is repeated until the configuration of such a model is clinically acceptable. And typically, this will be done within 2 or 3 iterations. And we at the ML Service Department, we will help you with the model configuration and the clinical go live of deep learning planning model. But even after you selected a model, we will be there for you to support you in using machine learning planning in RayStation. So in the configuration, for example, as I said, we will help you adjusting to match your clinical protocol. We can include information about your default beam set information, including the machine, the beam setup, the beam energies, machine constraints, and so on. But we can also have a look at workflow improvements. For example, automated ROI algebra can also be included in the model settings. And when you decide to go live, there will be a which is called commissioning. And for that commissioning part, it is essentially evaluating once again the model output of the final model before you go live, just to make sure that the quality is as expected. We will provide you with automated scripts for plan evaluation, where you will extract quantitative information about the monitor units, the clinical goals, and so on. And then you will feed this information into a template that we will provide you with for model evaluation, where you then score the output before you go live. But also when you went live already, you are encouraged to reach out anytime. That might be for support cases because you're running into an issue, or there's suboptimal model performance on a given case, which will then help us to understand what is to be tweaked in the model settings. But also just the reports on model performance is something that you can send us and provide us with. Over the course, we will release new models, and probably your clinic will update RayStation sometime in the life cycle in the future. So if you are using machine learning planning models already clinically, we will help you upgrade the model settings to the new version, and we will verify plan quality in the new RayStation version for you as well. So these are our core values and the key values that are implemented in how we do machine learning planning in RayStation. So we are a dedicated team of real people to find the best solution for patients with you. It's innovation in the way that we implement machine learning planning in RayStation, which helps us to use machine learning planning in everyday clinical practice. And it's a solution-oriented way of developing such a product, and will help us in making machine learning planning the best possible tool for you as an informed customer. But this is, of course, vice versa. So we also depend on your feedback to make the best of such models. And that's it for the insights in machine learning planning in RayStation. Thank you very much.
Thank you, Christian. Thank you a lot. I really hope that the whole part of your presentation gave us all in the webinar a very good understanding of what we have already achieved and managed to develop and release and be in the clinics. And coming back to the expectation question that I just asked just before Christian started. Yeah, you can see it. We do have some of these expectations already delivered to you. So it's just a matter of building the trust and building the processes of how to take the best use of these innovations that we create here at RaySearch. Now, to feel safe about these innovations, of course, it all goes to the point about quality assurance and validation. So this is where I would like to ask you another live question, two questions to be fair. So the first one is, so what is your current process for validating new AI solutions, if you have any in your clinics? So here we have couple of options for you. So it's either formal, structured QA processes that you already have managed to implement in your clinical workflows. So that would be the first option. The second one would be just ad hoc or informal approach. So you do have some processes covering the quality assurance and validation, but not a formal or structured. And the last one is there is no validation yet. You're just about to get started, or you would like to get started. Yes, so that's the options for the first question. We also have a second question in this poll, which asks you, how many patient cases would you test a new dose prediction model on before clinical use, if you would have an opportunity to implement one? And then here we also have some ranges for you to pick. So it's less than 5, from 5 to 10, from 11 to 25, or above 25, or you're just not sure because you have not had enough experience with AI dose prediction models just yet. All right, so while I was introducing the questions, your answers are coming in, which is super nice to see. And you know what? These answers are not only for my eyes, so let me share them with all of us and hear what we have. So when it comes to the first question, that makes me happy to see that the third of you do have formal structured QA processes. That's great. But the majority of you still have no validation yet, just getting started. And that's completely fine. We are with you on this journey. As Christian said, we do feel a lot about solution ownership. So if you want to get started, just let us know. And then the second question, you can see it yourself. The majority of you would go in between 11 and 25 patient cases. All right, so that was that. And I think it's time to go back to you, Fredrik, and see what else you have left for us today.
Great, thanks, Marta. So I must comment, I kind of noticed on a couple of these questions with the different alternative numbers that we get. Quite funny. And on the expectations on the plans, 11% I think was it should always be perfect. And that puts, of course, that's interesting, puts pressure on us, of course, to deliver. But we also have customers with running models where a majority of the plans are, I mean, basically used as is after review without any manual changes. So yeah, very interesting results, these ones. I will share a few slides in this later part of the webinar on kind of user gains and future directions in AI planning. So starting with user gains, the way we view deep learning planning is that it's a technology. it can help save time. So it's offline, you can script it, it's all automated, and in minutes you will have created a deliverable treatment plan. You can use it as an ideal starting point and so on. You don't have to sit there and click, you just review and refine if needed and QA. This will also help to standardize the process. Because if you scripted the whole thing, and if you use then AI models for this planning process, you will always have the right structure names, the same way of doing. The risk of manual human mistakes is reduced and so on. And we have done customers having done this full automation, and they basically report this. Augmented planning, I kind of alluded a bit to this before, but I mean, with automation, with fast automation, why don't generate 5 or 10 different plan alternatives, looking at different protocols, maybe different treatment machines, different trade-offs, browse through them. There's Plan Explorer and RayStation as a UI to do this in an efficient way. And then you select the one you like the most. And you can also utilize that in the longer run as, I mean, if you have 5 treatment rooms with different machines, which room should this patient go to, basically? So I think this automation enables this kind of thinking as well. And future-proof, I mean, who doesn't want to be in the front? And I think if you run the clinic with AI automation, you are in the front, and you will basically push the limits together. Oh, there's another poll.
Yes, there is. Yes, so, and this poll is about a word that's been mentioned many times already, and that's automation, right? Because there is no point of deep learning planning without automation. That's the whole essence of it, right? So let me ask the question for you about automating planning methods. So let's say if you would have access to a fully automated planning method now, what would you feel most confident using in the clinic? So here we have a couple of options. So, and I'll give you a bit more time to go through them and read them through. So the first one would be, of course, the knowledge-based planning. So when you use prior high-quality plans as models, so that's one automation approach. Another approach would be AI-based dose prediction. So that's basically what we are covering today, being implemented in the overall end-to-end automation solution. So third option would be template-based automation. So when you have a predefined planning protocols at your clinic. We also have a rule-based system. So that's the logic-driven planning with fixed clinical criteria. And then we also give you that option of fully automated planning. So that end-to-end automation with just minimal human input. Maybe you already feel comfortable about having this approach in your clinic. And of course, the very last question is, I'm not confident in any yet. Prefer manual or semi-automated approaches, which is completely fair as well. Yes, so these are the options about when it comes to the automated planning method. I'll give a couple of few seconds for you to pick your automation approach. All right, then let's see the results. I mean, the results quite, they make me happy quite a lot. So it's the AI-based dose prediction. I mean, we are targeting this audience, I guess, here today if we're talking this. So that's the majority of you, 31%. So yeah, thank you. And let's see if maybe someone is using that already, right, Fredrik?
Yes. Oh, what a coincidence. End-to-end automation with AI. So let's just comment on this briefly. I mean, this is the end goal, right? I mean, you automatically trigger the deep learning segmentation from image acquisition. You use structured templates to create structures based on those deep learning structures. From there, you automatically, pick the right protocol in the system, including the treatment machine, beam template, and so on, or maybe a set of those for multiple plans. And then you use an automated approach to create the treatment plans with deep learning. And this is not the future. This is actually happening. And then, as we have said, there is a human in the loop, of course. It's not a self-driving car, and there will be a person reviewing, refining, selecting, quality assuring, and treating. But the takeaway here is that deep learning segmentation and deep learning planning sticks together. I mean, it makes so much sense to connect these two technologies together. We have customers having implemented this clinically for prostate and breast treatments, and there will be more sites to follow, I'm sure. And if they can do it, you can do it. I think that's the take-home message of this slide. Some reflections. I mean, it's been a bit more than 5 years since the first clinical use of deep learning planning happened. That was at Princess Margaret Hospital in Toronto. So what have we seen? What have we learned? Big discussion. It's still ongoing. It will continue. Central ML models, basically, we validate, release it, it's locked, versus site-specific ML models. So when we started out, we believed local models were the way to go. Then we changed our mind. Why did we do that? Well, there were practicalities, there were regulatory reasons, there were, I mean, how can we control the quality out there and so on. And we also gradually realized how important the treatment plan quality is and the harmonization of the plans used for training and validation. Another aspect here is that we have seen this happen, and where basically a clinic gets a model that was based on a protocol from another clinic, and they basically run it and say, look, this is as good or better treatments than we do today for this patient cohort. Let's use this model and this protocol instead. So this is kind of starting the kind of flow of harmonizing treatments, basically through the deep learning planning models, understanding how other clinics treat their patients. But having said this, technology is evolving. Can we see a future where foundation models are applied and released, where there is some local fine-tuning? Yeah, possibly. We'll see. So go-live process, quality assurance. This is, of course, I mean, we are here to develop technology that makes a difference out there, that is clinically implemented. Super important, of course, topic for us. And while we validate in-house prior to release, these models must be tested on local data prior to clinical use. And that data set is very important to keep. And so you can compare when there's new versions of models released and so on. Maybe you have failure cases, then you want to put them into that data set to see if the next version of the model is more robust, and so on and so on. This is interesting. Opinions on dose shapes vary due to the subjective nature. We have seen that many times where even though a treatment plan fulfills all the clinical goals, all the quantitative aspects are fine, there is something about the dose shape that is different than how it used to be. So I think it's important here to stay objective, perform quality assurance as for any other treatment plan, and look at what actually matters in the treatment plan and for the outcome of the patient. And that comes to the final point, and it's important to analyze which manual changes to an automated plan that make an impact and make a difference. So we have clinics reporting that, okay, they have been very ambitious projects looking at automated AI plans, how many were directly delivered without change, how many were manually changed, and how much difference did those changes make. There is definitely evidence that, okay, there were changes made, but they did not make any impact. So important to track that. Where is this going? Definitely increased model coverage, more coverage, more protocol supported. More general dose prediction models go away from protocol-specific models. Yes, that's a trend coming. Prediction of treatment delivery parameters. So to remove this optimization step and just from the input predict parameters of treatment machine. Maybe there's definitely research. We do method studies on this, and there is publications on this. Foundation models with local fine tuning. Yes, that was on the previous slide. That could be a direction. Model performance monitoring for sure, just as for the deep learning segmentation. Super important, not only to commission the model before clinical use, but also monitor performance over time. And to the point of Clinic A adopting protocol from Clinic B? Will AI help drive the harmonization protocols and enable more standardized care? Hopefully, in my opinion. And we see some initiatives in countries. I can mention the Netherlands, I think is a good example, where clinics go together, compare automated AI models across clinics and so on. I think it's a super interesting direction. So where does this leave us? Some overlap with last week's webinar, actually, but some differences as well. AI is widely used in radiation oncology. Yes. Implementation is key. Yes, for sure. Clinical implementation of AI-driven automation will continue up. Yes, that is also true, and we will see that continue up. And finally, it's not about why and long. I think it's about how, and we should definitely work on that together. How do you go live? How do you improve the performance over time, and so on? So with that, we have another poll.
Yes, a very final one, because as you, Fredrik, did like very nicely summarize, I think both sessions that we had last week and this one that we're having right now. And then talking about that how, for me, that how is all about trust, right? Trust between us as the providers of these solutions and the users, you of these solutions. And then we started this whole series with asking you while you were registering about trust. What is your level of trust in AI in general? So now we're here after these two sessions, and I would like to ask the same question once again, just slightly differently phrased. So, how has your trust in AI changed after the two RaySearch webinar sessions that we had last week and the one that we have having right now? And we're giving you these options. So we hope, I hope, we all hope in a team that we have many here in the webinar today and behind the screens as well, that it increased. So you feel more confident in AI's role in the cancer care. Stayed the same. So my trust level hasn't changed, which is fair enough. It's a work in progress always, or decreased. And then the second question is just for you to hear out. Is it something valuable for you, the sessions that we have here, the webinars that we offer for you to our community here? So just a simple question, would you be interested in attending future RaySearch webinars on AI? We are planning to have more of them, just a little sneak peek, or just in general, more webinars to offer you. All right, so let's end the poll and share the results. All right, so when it comes to your trust level, I'm happy to see that it's only one person who has the a lower level of trust in AI up to these two sessions. That's fair enough. And many of you has a better trust, which is good. For half of you that stayed the same, which is also good. It's again, work in progress. And the majority of you would like to have more sessions of these. So that's good. All right, so when it comes to the Q&A, you can definitely see that we're running over time. But you know what? That's why we have the four of our experts joining us in live webinars. So if you take a look at the Q&A tab, there's almost no questions left. And if there are any unanswered questions, we will make sure to answer them and send you a link after the webinar, where we will cover any unanswered ones, also the ones that you pre-submitted. But I think we tried to cover these questions while we are presenting. All right, so here we are, and so that's the officially, let's say, the end of these two sessions on artificial intelligence in cancer care. But we're not stopping here, right? We have so many more planned and in the future, and then we even breaking new ground. That's how we phrase it here. So for the upcoming webinar, so what we're doing, so we're going from a screen digital format to actually a physical one, and that's not relevant for all of you who are here with us today, but for some of you it might be relevant, because what we do, so RaySearch webinars, we go to Astro, which is happening just in a more than a week, next weekend. So we're gonna be there at the RaySearch booth, and we'll be having some talks, some discussions, some presentations, So you're more than welcome to join us there at our booth number 800 if you happen to be in Vienna next weekend. We will be gladly waiting for you to keep the conversation going and cover even more topics. So yes, so that's it from us today. Thank you so much. We will share the recording. So please go back, rewatch, send us all the questions. We're here to listen and we're here to learn together. All right, have a lovely day, everyone.
Bye. Thanks.
Thank you very much.